Hello everyone, my name is Zhao. Today I will be talking about how we push RF-based 3D SLAM to match the performance of vision-based methods. This is joint work with Zhao and my advisor Ming. Today we live in a world filled with intelligent systems like robots, autonomous vehicles, and more. These systems rely heavily on vision sensors, such as cameras, to perceive their surroundings. However, in harsh environments, vision sensors can struggle or even fail, leading to potential safety risks. Fortunately, radio frequency sensors can sense through occlusions and operate robustly under challenging conditions. The advantages of RF sensing have attracted significant attention within our community. Since then, extensive research has advanced the field from traditional detection towards visual perception tasks, including imaging, pose estimation, human mesh reconstruction, etc. Among these visual perception applications, SLAM stands out as a crucial task that enables robots to operate safely in large-scale 3D environments. Many core aspects of robot autonomy, such as navigation, path planning, and collision avoidance, depend on accurate localization and mapping. Because of its importance, researchers have been exploring how to use RF sensors for SLAM. But so far, there is still a big gap compared to vision SLAM. Current RF-based methods can only build 2D maps with coarse resolution. However, visual SLAM has long been capable of producing high-quality 3D reconstructions. These limitations have slowed down the adoption of RF SLAM. So we ask, can RF-based SLAM ever reach visual level quality? This is exactly what I'm going to show you. I will present CartoRadar, an RF-based 3D SLAM system that achieves both high-fidelity mapping and accurate localization. With these results, our system is even rivaling vision approaches. So, how can we do that? To reach this level of quality, we built on our previous work, CartoRadar, an RF imaging system that has sub-degree resolution. It works by rotating a millimeter-based radar to create a dense synthetic cylindrical array. Using 3D beamforming, we obtain a detailed 3D RF heat map. Then a network further enhances the elevation resolution and produces a dense range image. But is this enough for high-fidelity 3D SLAM? Here is an example of a radar point cloud. While it looks similar to LiDAR output, you can probably notice some noisy points in the predicted results. This becomes clearer when we look at the CDF plot. Most points are accurate, shown by the small medium arrow, but the 90th percentile arrow is about 10 times higher, creating those noisy outliers. In fact, this kind of long-tail arrow is quite common and also appears in many other learning-based RF sensing systems. If we simply run LiDAR-based SLAM on these noisy radar point clouds, it won't work. That's because this method treats every point equally. But if we could somehow figure out which points are more reliable, we might have a way to manage the arrows. And this is the uncertainty quantification in machine learning literature. Now, in the context of learning-based RF imaging, we are dealing with an underdetermined system. Let me explain what it means. In this example, there is an elevator. Because of specular reflection, the reflected signal is weak in the heat map. In another scenario, an open area can also produce a very similar pattern. So, as a result, when the model makes predictions, it faces high uncertainty in this region. But not all areas are equally uncertain. For instance, in this wall region, the radar receives strong reflections, allowing the model to predict accurately with low uncertainty. This observation led us to explore sensitivity analysis as a way to quantify the uncertainty. Let me illustrate how we do this. In this example, we show the heat map, the model's prediction, and the corresponding arrow. Notice that this region shows a large arrow, which should have high uncertainty. Now, we introduce noise to perturb the heat map. The model gives a new prediction, and we observe that this region changes significantly, indicating high uncertainty, while the other region remains stable, indicating low uncertainty. Therefore, to quantify the uncertainty, we repeated this process several times and computed the variance of the noisy predictions. This gives us per pixel uncertainty estimation as a proxy of the error. Worth mentioning, our approach is training-free, which doesn't require modifying or retraining the model. Now that we have quantified the prediction uncertainty and obtained point clouds with per point uncertainty, the next question is how this uncertainty tells us a point in the space is occupied or not. Let's look at a point cloud. For each point, the uncertainty describes how likely its position is along the range direction. We assume this follows a Laplacian distribution. If we sample position I at distance Si, then for it to be occupied, the true surface must lie somewhere within this range. We set the width as 2 epsilon, and the occupancy probability can be calculated by integrating within this interval. On the other hand, if it's unoccupied, the true points must lie beyond this range, and the corresponding probability is again given by the integration. For these equations, we can see that if we cast ray into the scene and sample points along the ray, we can calculate whether each point is likely to be occupied or not. So a natural next step is to learn an occupancy field. For every sample point, we feed it into the neural network to get its estimated occupancy. We train this occupancy field in a probabilistic way. For each point I, we use the binary cross-entropy term weighted by the corresponding occupancy probabilities. By giving each point direct probability supervision, our approach correctly handles noisy points and has fast convergence. So far, I have shown our core components. Now, I will show you how we deal with online streaming data and improve runtime efficiency. For incoming IF signals, new frames including point cloud and pose will be appended in the corresponding queues. At each step, we will select the latest frame and a randomly selected historical frame to train our implicit occupancy field. During training, we allow gradients on the poses so they can also be updated for better geometry alignment. To correct drift, we also include a loop closure detection module which will update the poses when a loop is detected. Finally, with the trained implicit occupancy field, we can render a 3D map of the environment. We implement our system by rotating a millimeter-wave radar with a motor and add a 3D LiDAR for ground truth reference. To provide mobility, the setup is mounted on the mobile robot. We collect our datasets by driving the robots around 14 floors across 5 buildings with a total traversing distance over 1.5 kilometers. We first evaluate our uncertainty quantification performance with other baselines. All baselines methods require retraining the model. Our training-free approach not only gets rid of the retraining process, but also achieves better quantification performance. we visualize the results while the robot is moving. Our robust IF sensing module predicts range images that follows the LiDAR measurement and estimates the uncertainty that follows the range estimation error. Now we evaluate the SLAM performance by comparing vision baselines with our methods. All data were collected along the same trajectory, and the results are benchmarked against LiDAR ground truth. For both localization and mapping, our method achieves the best performance, reaching a level comparable to vision approaches. Here are some visual examples for comparison. Due to limited FOV and failure to capture transparent objects, vision methods miss reconstruction in many regions, while ours successfully capture them. Here we visualize our centimeter-level localization and high-fidelity mapping results. You can see ours is closely aligned with LiDAR ground truth. And this is another example. We also test different system components to see their contributions to the mapping details. For uncertainty only and joint optimization only, both cases show effective improvements. And when they are both enabled, the performance can be further boosted. These high-fidelity details are clearly revealed in the map, such as chairs, elevators, irregular structures, and stairs. Our results even show the steps in the stair. Besides performance, our system is also very efficient. It reaches 95% of the final F score with only 2 seconds of training. To conclude, CartoRadar is the first IF-based 3D SLAM system that achieves centimeter-level accuracy and high-fidelity details. With our novel training-free uncertainty quantification and effective uncertainty-aware SLAM, CartoRadar is rivaling vision approaches. We believe this opens up new possibilities for robust perception in challenging environments. So, to facilitate future research, we have released all codes and datasets on our website. Thank you for your attention.